Good morning, Diman. Good morning, Chris, Ethan. Good morning, Atun, Yona, Itamar, Becky, Sylvie. Good morning, Justin. Hey, Sarah. Hey, Jacqueline. My apologies. This camera is really finicky. As when I try and set it up and plug it in and turn it on, I do it the same way every time, and it's always a 50-50 shot of whether it actually registers on my computer or not. So what's the solution? I gotta start prepping this at 9:30 instead of 9:50, I guess. Good morning, Ayanava. I hope your weekends were super nice. All right. Okay, so there's 15 of us in here. I think that's enough to get started. But let's just wait one more minute, right? So we've been live for 4 minutes. Let's give one more minute for, 17, very nice. Better. Oh, it went down to 16. Oh no. All right, I'm gonna start drawing the first problem. Okay. I'm gonna move it this way. And go this way, this way, this way, this way, this way. Okay, good. Okay, so hey, Grandmaster to you too, Ethan Young. All right, let's get started. I'm just gonna adjust some stuff for you guys. All right, cool. So this is just a homework review that it can turn into a lesson when we start to go. Oh, it will turn into like a very mini lesson because there is a small reflection I'd like you to do now that we see the thing. All right. So the first circuit is really simple. It's just a 6-volt battery. I hope you have yours in front of you with you so we can kind of go over these together. And I have a 2 ohm resistor and a 1 ohm resistor. All right, so this is 6 volts. And this is 2 ohms, and this is 1 ohm. All right, so the first thing I want to do is I want to make this equal to an equivalent circuit. with 3 ohms and 6-volt battery. I know this because they're just in series, and for the whole series thing, your equivalent resistance is always just R1 plus R2 plus R3, etc., right? How many ever things you have, okay? Now doing this, if I use my loop rule and I gain 6 here, through this resistor I lose 6, right? So through this resistor I can say V is IR, and I'm losing 6 volts, and that's equal to the current times 3 ohms, right? So I know the current is 2 amperes, all right? So if I make my VIR chart, 1, 2, total, I know the total loss is 6, the total current is 2 amperes, and the total resistance is 3 ohms. And I know this is 2 ohms and 1 ohm. If there's 2 amperes current going through this whole circuit, then there's 2 amperes of current going through here, and that means this resistor gets 2 amperes, this resistor gets 2 amperes. Boom, boom, and I have 4 volts, and I have 2 volts. All right, so hopefully that's what your first solution should be looking like. All right, let's move on. Okay, the next one is, this is going to be really fast. Wow, okay. And if you are a little bored, I don't blame you, because once you do like 3 of these, it gets to be the same. But don't worry, if you stay with me, all right, I'm going to give you a much more interesting assignment in which you are going to use your results from this worksheet, okay? So this is 3 ohms, this is 9 volts, this is, I don't know, but I know I have 2 amperes of current going through here, all right? So we can make our VIR chart again. 1, 2, total. I know my total drop is 9 volts. Am I getting that from the battery? Yes and no, right? This is not the voltage of the battery, but I know if I turn this into an equivalent circuit with only 1 resistor, then I know that has to lose 9 volts because the gain's 9 volts here, right? I know the total current is 2 amperes, and that's the same here, right? I have 2 amperes going through here, I have 2 amperes going through here, that means I have 2 amperes going through here as well, okay? Yikes, look at that smudge. And then I know for the second resistor I have 3 ohms, and oh my goodness, look at this, that means it has 6 volts. That means this had to have had 3 volts. Oh, so first of all, there's a lot of things I could do from here, right? The first is to calculate the resistance here. This would be 4.5 ohms due to Ohm's law, right? 9 equals 2 times 4.5. And then using my equivalent formula, I know, oh, this had to have been 1.5 ohms, right, if I add those. Or I could have said, oh, look, if the total voltage is 9 here, and wait, if this is 6 volts, and I gain 9 here, that means I had to lose 3 volts here, right? So 3 volts, and then I get 1.5 ohms that way. There's a lot of ways to solve number 2, right? It's a very flexible problem. All right, number 3. Cool. All right, so we are just gonna straight up do this. Pop, 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 pop. Okay, cool. And I have 30-volt drop here. Wow, huge. Okay. I also have 15 ohms here. And I don't know the voltage of my battery. Whoa, okay, cool. So we can again do a VII chart. Wow, this is our favorite tool. Okay, 1, 2, 3. I don't really like to use these to solve out, but what I do like about these is it's really easy to show and check your work, right? So as I was looking through your turned in assignments, like all I have to do is look at the chart and I can see if you got it right, okay? That's why I like doing this. So V1 is 30, R2 is 15, and I2 is 4 amperes. All right, so because I know it's in a series circuit, I know this is also going to get 4 amperes, right? If there's 4 amperes traveling this way, that means there was 4 amperes traveling this way. And that means in my equivalent circuit, right, I would have also had 4 amperes just traveling, right? It's just one branch. So I know my total current's also 4 amperes. Cool. Then what? Well, what can I solve for? It's almost like Sudoku, right? I can only solve this one because this is the only row. Oh, I can solve for this one or this one. So I'm just going to do this one. This is 60. Right, I could have done this one as well. And then that would have made it 7.5, right? Yes. And then if I did it this way, then I can find my total resistance, which is just 22.5 ohms, or I could have gone this way first, and I would have found it's 90 volts. And I could have divided 90 by 4 to get 22.5, or I could have multiplied 22.5 times 4 to get 90 volts. All right? Cool. Let's move on to number 4. Okay. I will move on. Ooh. Can you guys tell this one's spicy? Because it has how many resistors? It has 3. Wow. So fun. Okay. So I have a resistor here, I have a resistor here, and I have a resistor here. Cool. And this is 45 volts. This is 10 volt drop. This is a 20 volt drop. And this is a 3 ohm resistor. Wow. Okay, so I'm going to go 1, 2, 3. All right. So 1, 2, 3. Oh, I labeled it that way in the problem too. All right, cool. So I can do V, I, R, and I have 1, 2, 3 total. So a lot of givens, right? Because my battery is 45, and by gaining 45, that means from here to here, I'm going to lose 45, right? Lose something, I should have lost 45 by the time I come back. So I know the total drop is 45 volts. Okay. And I know my resistances, I don't know the resistances, but I know I lose 10 volts here, I lose 20 volts here, and my resistance here is 3 ohms, right? I think it's clear to see which one you can solve for first. It's just this one. You're going to use the loop rule, right? If I have to lose 45 somewhere, and I've only lost 30 here, I have to lose 15 here, okay? Now what can I solve for? Oh boy, I can solve for the current, and it's 5 amperes, and I know then if 5 amperes is traveling through this one, it was traveling through this one, it was traveling through this one. This is all one branch. And if I simplify it into a single branch equivalent circuit, since this is one branch and this is one branch, this also still has 5 amperes on it. So remember, this total is not a total. It is the total voltage. It is the total resistance, but it's not the total current, right? This is really not a total. This row is only for the equivalent circuit. Okay, I need to emphasize that, especially based on what we're going to learn tomorrow, right? So now what? I mean, you can just use Ohm's law 3 different times to find the resistances. This will be 2 ohms, this will be 4 ohms, and then this will be 9 ohms. And you can double check. Do these 3 add to that one? Yay! Awesome. Okay, so what does that mean? We're all a bunch of stars. That's what that means. All right, so let's keep going on to number 5. Okay. It's got to scroll there. Okay, cool. So now we have this right? And boom, 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 do 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 do, do 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 do, do 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 do. Okay, and I did tell you about typo, right? This was V3, and that should have been 30 volts. My bad. Okay, this is R2 equals 8 ohms, and R1 equals 10 ohms. Okay, and I have 5 amperes running through all of them, right? So I can do VIR again. 1, 2, 3 total. Okay. What says 9? Yes, that is a 9. Okay. Oh. Okay, so let's go over the. I know all 3 have 5 amperes running through them. Likewise, the total current is also 5, because if I simplify it, it's just 5, right? I know V3 is 30. I know R2 is 8. And I know R1 is 10. All right, so just from this, if I see 5 amperes going this way, boom, and I know these resistances, oh, come on, right? So this is obviously 40 volts, and then this is obviously 50 volts, right? And if that's 30 volts, then I know the total voltage was 120 volts, right? So the total voltage drop is under 20 volts, which means my battery, what I gained was also 120 volts as well, right? So I can write 120 volts here. And remember, is this the battery thing? No, it is not. It is not, right? It is just how much I lost through all 3 of those. So I didn't even have to write that. I just kind of included it because some people like seeing how much voltage the battery gives, right? So I know this is 50 volts. I know this is 40 volts. And then boom, right? So once I know that, right, and I know this voltage and this current, I could have also immediately solved for the resistance, right? And it's 6 ohms, right? Because if I have 5 amperes going through here and I'm losing 30 volts, I can use V use IR, and the R is 6 ohms, right? Okay, so yeah, and then my total thing is 24 ohms. All right. Here are some reflections I'd like you to do, and these will be due tomorrow. I mean tonight. Okay. You're only gonna have 2 assignments this week. All right. So kind of calm down. Can you guys calm down, please? Okay. So the first thing I want you to realize is like, what are some rules, right? What were some shortcuts that you used, or some rules that you noticed every one of these circuits followed when you plugged it into your V equals IR chart? I want to invite some of you to just type that up in the comments. All right, write in the chat. Just say like something you noticed, something you could always like automatically do, or a rule that you noticed that all these were following. Yeah, so the first one is it's all the same current. All right, so there's our first observation, right? Every element experiences the same current. Okay. It's okay. He just got you by a couple seconds. The resistances all add up to the total, right? The total resistance is the sum of all individual resistors. And yeah, this is only for series. Only for series. Okay. One more observation, everybody. What did you notice? For each of these 5 circuits, which resistors always had the larger voltage drops? Look at your answers. Which resistors had the largest voltage drops consistently? There's a rule being followed, always. Thank you, Sylvie. Thank you, Chris. Thank you, Itamar. Right? Yeah, it's the resistors with the highest resistance. Right? No matter, yeah, in all of our circuits, right? Even this one is 50, 40, 30. Look at that, 10, 8, 6. Right? And this is going to be true for every circuit, as long as it's a simple series circuit. Right? So the resistors with higher resistance consistently experience larger drops in voltage. Okay? And here's your assignment. I want you to ask why this is true. All right? So for the first one, every element experiences the same current. Well, why is that true? Junction rule. Right? If I treat that as my junction, the current going in equals the current going out. So that means the current going in, this point, which was the current going through that resistor, equals the current going out, which is the current going through that resistor, right? So the junction rule perfectly explains why every element experiences the same current. Total R is the same for is the sum of the individual resistors. That's because for elements in series, the equivalent resistance when I treat individual multiple resistors as one is simply just the sum. And that's why that works. The third prompt is your homework assignment due tonight. It's a paragraph length response. I thought we were done with those. I don't think so. Do you know why we're never done? Because stars are never done. You guys are stars, okay? And you know what? Stars always get pumped up to write paragraph length responses. All right, so get pumped for paragraphs, my star students. Yeah, I want you to write a paragraph length response about why resistors with higher voltages experience larger drops in voltage, right? You can use the first thing, right? You can use that they all receive the same current. You can use Ohm's law, stuff like that, right? It's a pretty simple response, I think, right? Do you guys have any questions on that before we move on to the parallel worksheet? Oh, deep, Chris. My counter argument for that would be not within your lifetime, buddy. Thank you, Diman. My thoughts exactly. let's move on to the second sheet, okay? Whew. All right, number 1, we have 60. And if you guys have been thinking about it, you're right. There's going to be a very similar paragraph length response in response to parallel circuits as well. Okay. Wah. I know. I'm sorry. Oh, that's a terrible one. Oh my gosh. Okay, so I have 20 ohms here. I have 30 ohms here. And now I have 60 volts. All right. So if I want to make this equal to an equivalent circuit, with just what is that, right? Well, it's given by 1 over REQ equals 1 over 20 plus 1 over 30. And then this is equal to, I want to say 5 over 60. Yep. Which would imply REQ equals 12 ohms. Okay, so I know this is 12 ohms. Nice, now I can start solving stuff. Get pumped. Okay, so I have VIR, and I have 1, 2 total. I know my total voltage is 60. Why? Because if I gain 60 here, I lose 60 there, right? So, and this row, remember, is always about the simplified equivalent circuit, all right? The SEC, the Securities and Exchange Commission, okay? To know the response is probably due Friday. Yeah, we're gonna give it some time, all right? No reason to overwhelm you guys with too much work, okay? All right, so, and let me write down the stuff I already know. This is 20 ohms. This is 30 ohms. That's about it. Oh, my total resistance is now 12 ohms. What? It's not the sum of 20 and 30? No, no, no. It isn't that. Okay. So what can I solve for now, right? Oh, if I know this is 60 volts, and I know the resistance is 12, I can finally solve for the current going through here. Okay, and then that is what? I think it's 5 ohms. I mean 5 amperes. Yay. Does that mean I can just do 5 and 5 here? No, because this is a parallel circuit. So, hell yes. Yeah. So if I have 5 amperes going through this way, I actually now have a guarantee that both of these are less than 5, right? Because the 5 has to split up at this junction right here. How does it split up? I do not know, okay? So to do this, we actually need to solve for the 2 voltages first. Let me take this. If I gain 60 here and I take this path and then I come back, how much did I lose there? Oh, 60. If I gain 60 here and instead my electron went here and it lost something and it came back, how much did it lose there? Oh, 60. So they both lose 60 volts. Again, this is not the sum anymore, right? It was never the sum. The sum was never a rule. It was a coincidence for our series circuits, okay? It was not a rule, it was a coincidence. It was a coincidence that our equivalent circuit, this one, had the same, its voltage was the same voltage as the multiple ones combined. In this one, the coincidence is no longer there. I lose 60 volts here, but guess what? They both lose 60, okay? Yeah, now I can see 60, this is 3 amperes, right? And then this is 2 amperes, right? 60 volts, 30 ohms, obviously 2 amperes. 60 volts, 20 ohms, obviously 3 amperes. And look at that. This is the column that adds up now, isn't it? Right? Because, oh, if I add 5 amperes here and 5 amperes here, of course, these two currents need to add to 5, right? Cool, cool, cool. All right, let's keep moving. 120, 120 volts. And boom, 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 boom. Boom, 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 boom. All right. Boom, 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 boom. Boom, 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 boom. And I have 1 ampere here. So let's do a VIR chart again. 1, 2 total. I know this is 120 volts. I also know, hey, if I gain 120 here, I lost 120 there. If I gained 120 there and instead I take this path, didn't I lose 120 there as well? Yes. Okay. Hopefully we can start to see some patterns now. I know this is 3 amperes and 1 ampere. So I know this is 4 amperes, right? Because how much current is there? How much current is there? Well, that's 4 amperes, isn't it? Because I have 3 and I have 1. Right? And at that junction, the current going in must equal the current going out. At this junction, the current going in must equal the current going out. Now I can just do Ohm's law, boom, 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 right? And this will give me 40 ohms. This will give me 120 ohms. And this will give me 30 ohms. This should make sense too. If I do 1 over 40 plus 1 over 120, this actually does equal 1 over 30, right? So there's another way to check your answer there as well. Okay, cool. We can keep on double checking. Is 30 less than 40? Yes, right? And I want my equivalent resistance to always be smaller than the smallest resistor for a parallel series, a parallel circuit. Remember that? Is the junction rule being followed here? Yes. Do my two things in parallel have the same voltage? Yes. Okay, cool. Let's move on to number 3. Here I have a whoop, 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 whoop. Okay, and whoop, 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 whoop. Okay, cool. And this is 12 ohms. This is 18 ohms. And instead of number 1 where I gave you the voltage, now I give you the current here. And this is 5 amperes. Cool, so I have VIR again. And I have 1, 2 total. And I don't know the voltages. I know the current here is 5 amperes. I know the resistance is 12 ohms. And here's 18 ohms. So the first thing I can do is I can transform this into a single circuit again. And that's 1 over 12 plus 1 over 18 equals 1 over R. That's 5 over 36. Ew, did I really give you this? I'm so sorry. Ew. Okay, so R, the equivalent resistance is, what is 7.2? Yikes. Okay, so this is 7.2 ohms. Very sorry about that. So now I know the loss of that resistor, right? How many voltages did I lose? I lost 36 volts. Okay, which means I gained 36 in my battery. Okay, which means if I gain 36 in my battery, then here if I gain 36, that means I lost 36 here. And if I gained 36 here, I lost 36 there, right? So they both lose 36, right? Now I can solve for the currents, right? I know they add to 5. How do they add to 5? This is 3, and this is 2, right? Just using Ohm's law. Cool. I hope you guys really notice, all 21 of you in the chat right now, how I solved the 36s out, right? I solved for the equivalent resistance that was 7.2 ohms, and I know since there was 5 amperes of current, the voltage drop had to be 36, which meant the battery was 36. Notice after that, I didn't just go 36, 36, 36, all right? That's not a critical way and a correct way of looking at the circuit, all right? Instead of saying, oh, that voltage is 36, let me just do 36 across the board. Listen carefully to what I did. I'm just gonna say it again so you guys don't have to rewind this video. I determined the voltage drop was 36 due to Ohm's law. Due to the loop rule, if I lost 36 here, I had to gain 36. I did not move on to there. Instead, I said, oh, that's 36 then, because that's the exact same battery. And if I gain 36 here due to the loop rule, I lost 36 there. So I fill in 36. For this resistor, if I gain 36 here, I lost 36 there. So I plug in 36 there, right? Be really careful about how you apply your shortcuts, right? Not only are they shortcuts, there's a risk of that you lose the understanding there, right? If you didn't understand this part, you're in a little trouble going into tomorrow, right? So you got to look at it that way. Like the shortcuts are nice, but I think they're just nice to check the answers with. They are not nice to actually solve the problems with, okay? All right. The last two, all right, and then we can move on to our cool reflections, okay? Hold up, I am running a little late. I just have to email my Regents class saying they're gonna be a little late, okay? So just give me a sec. Okay, hold up. Whoa. Sorry. Oh. Wow, Mr. So, he's such a boomer. He doesn't know how to use Google Cloud. I do. I just gotta make sure something's okay first. Like, squeeze me. What? Oh, there it is. Okay. Okay. So sorry about the delay. All right, let's move on to the next one. Okay. So we have, what are we looking at now? A 20-volt battery. And 3 resistors in parallel, all right? Just to illustrate the equivalence, I'm going to draw a circuit that's identical to the one in the problem, but just with the circuit diagram looking a little different, right? Right? You got to convince yourself that these are the same, okay? I have 6 amperes running through here. Cool. All resistors are identical. Wow. Okay. So this is tricky. There's a lot of different ways to do this. I'm gonna do it this way first, right? This has an equivalent resistance of what? 20 over 6, right? So that is going to be 3.67 ohms, I believe. Right? Am I right here, or is that 3.33? It's totally 3.33. Okay. So now I know that 1 over 3.33 equals 1 over r plus 1 over r plus 1 over r. Okay. And why do I know that? Because they're all identical, right? So this is 3 over r equals 1 over 3.33. So I'm going to cross multiply. I have r equals 3 times 20 over 6. And this is now equal to 10. Right? So now I know now each of these are 10 ohms. And then they each lose 20 volts, right? Gain 20, lose 20, gain 20, lose 20, gain 20, lose 20. Why do I know that? Loop rule, baby, right? And if I lose 20 here, 20 volts equals the current times 10 ohms. The current for each of them is 2 amperes, right? All right. I'm not even going to write a VIR chart for that, right? Right now, but I do believe you asked around a week ago. It's like anytime I have a parallel circuit or anytime it splits up, or like how do I know when it's going to be equal? How do I know which branch gets more current, right? Well, now you've seen a situation where they do all get the same current. Like what condition must be met for that to happen, right? Don't answer that in the chat yet. All right, we're going to answer that as part of the assignment. Okay, last one. All right, so this is also 3 resistors. The battery's here now. Wow, mixing it up, Mr. So. All right, so I have this over here, okay? And I have 3 ohms here, 6 ohms here, and I have 5 ohms this way, and I have 2 ohms this way. Right. So I have VIR, 1, 2, 3 total. Okay. And what are we looking at now? My total current is 7. Right, I have 2 coming out here, 5 coming out here, which means the current in this section, then that's my total current, right, is 7 amperes. I know through the third resistor, it's 6 ohms, and I have 2 amperes of current. In my first resistor, I have 3 ohms. Already here, what can I solve for? Here, 2 amperes, 6 ohms, that's 12 volts. Oh my gosh, if that's 12, then I gain 12 in the battery, don't I? If I gain 12 in the battery, that means in this one I lose 12, so I can write 12 here. And if I gain 12 in the battery, that means on this one I also lose 12. Notice the justification I used to call each of those 12-volt drops, right? I'm not just simply going 12, 12, 12, 12, 12. That's a bad way to do it, right? What's my total? We know it's 12. Let's talk about why, right? The worst thing you can do in physics is to become automatic, okay? If this is a 12-volt battery, why is it a 12-volt battery? Because I gained 12 here. I lost 12 here. Why did I lose 12? 2 amperes, 6 ohms, right? So if I lost 12 here, I had to have gained 12 there. That's why I know this is a gain of 12. Then I lose 12 here as well, and that's my equivalent total, right? Cool. Already here, I can do the total resistance then of this resistor. But there are things we can do first, right? So 12.3, this is 4 amperes. So this is 4 amperes. Oh my gosh, if this is 5, then that means this is 1 due to the junction rule, right? So now, instead, I have 1 ampere here. Oh my gosh, that's 12 ohms. Right, so here I can do 1 over 3 plus 1 over 12 plus 1 over 6 equals 1 over r. Or I can just go 12 divided by 7. Guess what I'm going to do? 12 divided by 7. Okay, and yikes. That's a decimal I have not memorized. What is it? It's just, 1.8. Oh, Jesus. Okay, 12 divided by 7. It is 1.714. Okay, so 1.714 ohms. Okay. All right. All right, so any questions so far before we move on to our reflections? All right, so if that's the case, what are the shortcuts that we don't want to be using, but what are some patterns and trends that we noticed? All right, put them in the chat, please. There's 2 big ones I'm really looking for here today. Lowest current has the high resistance. All right, so there's two things I want to look at, right? So one, let's do the easier one, right? Each resistor had same voltage drop, okay? Two, each individual current added up to the total. And three is Chris's observation, right? And this is related to Ainava's question from a long time ago. Why don't the currents split up evenly? How do I know when they split up evenly, right? So the smaller resistors had larger currents. Okay? All right, let's talk about why. All right, so the first one, each resistor had the same voltage drop. Why? This is simply due to the loop rule, right? All right, let's do this loop. Okay, gain 12, lose 12. Let's do this loop. Gain 12, lose 12. Let's do this loop. Gain 12, lose 12, right? So all of them lost 12. Oh, whoa. Okay, sorry, so sorry. Okay. Each individual current added up to the total. What is that? That's the junction rule, isn't it? Smaller resistors had larger currents. Another way of saying this is the current prefers less resistance, right? It will take the path of least resistance. Right, so imagine like the hallway splits up into two different hallways. Where are more students going to go? Well, the hallway with less resistance, right? But I want you to write a more valid argument with smaller resistors of larger currents, paragraph length response, right? A hint, you're going to use loop rule plus Ohm's law, okay? In a parallel circuit, why do smaller resistors have the larger current? Okay. Likewise, I'll give you a hint for the first one. Okay. The resistors with higher resistance consistently experience larger drops in voltage. Why is that? You're going to be combining the junction rule. This is because they have, same current. And then plus Ohm's law, right? These are very short paragraphs. They can be 2 to 3 sentences, all right? So what I mean by a paragraph is not like, 4 to 5 sentences, topic sentence, supporting evidence, right? No, I'm talking about whenever you write, a paragraph should just be a complete idea. And that's what I want. I just want a complete fleshed out idea in writing. And if that's in 2 sentences, that's fine. Okay? That's your assignment. I'll be posting that on Google Classroom today. However, it is due Friday. Okay? Yeah, the electron current always travels in the same direction. All right. Any other questions? I would love to answer before I move to the next stream. Dr. Abrams, does she teach that too? I'm glad. Yeah, that is always how I was taught to write, so I hope that's how you're being taught to write too. What again is the definition of voltage? Itamar. Yeah, it's the change in potential. Right? So it represents how much energy I would lose in my circuit if I knew how much charge had passed through the circuit, right? Stuff like that. All right. With that, I will wish you a very happy start to the week. I hope you guys enjoyed the Bill Withers from Friday. I had no idea he had passed away when I shared that with you, but it made me enjoy it even more. Okay? All right. So with that, I will say goodbye, and I hope you guys are doing well. I mean that. Okay. Bye.